Hey everyone, and welcome. Today we are diving deep into a chapter that can absolutely make or break your chemistry score in the CUET exam: aldehydes and ketones. Let's get right into it. So let's be real for a second. Are you seeing questions on Tollens test or reactivity order in your mock tests and just guessing? Do you kind of get stuck trying to figure out what the product of a reaction is going to be? If that sounds familiar, don't worry. You are in the perfect place. Here's my promise to you. In just the next 10 minutes, we're going to flip the script. We're going to take this chapter from confusing to your absolute biggest strength. So stick with me till the end. So, what's our game plan? Simple. First, we'll see why this topic is a total goldmine for marks. Then, we'll unlock the one core mechanism that explains everything. After that, we'll cover the must-know reactions, give you an exam toolkit with tricks, and then wrap it all up with a lightning-fast final revision. Let's do this. Okay, first things first, why should you zoom in and give this chapter your full attention? Well, it's simple. This topic is an absolute goldmine for marks on the CUET exam. Look, the numbers don't lie. This isn't just some random chapter. It's a hot spot for questions every single year. The examiners love to test you on this stuff, predicting products, spotting the right reagent, or arranging compounds by reactivity. And the best part? If you nail this, you're also setting yourself up for success in alcohols and carboxylic acids. We're talking about a potential 8 to 12 marks just sitting there, waiting for you. Now for the master key. I'm serious. If you can understand this next part, you've pretty much cracked 80% of the entire chapter. It all boils down to one single core idea. And the star of the show is nucleophilic addition. That's the name you need to remember. The whole story is about just two characters: a nucleophile, which is loaded with electrons and looking for a positive charge, and our carbonyl carbon, which is electron poor because it's attached to that greedy oxygen atom. It's a classic case of opposites attract. So how does this whole thing happen? It's a simple two-step dance. Step 1, bam! The nucleophile attacks that slightly positive carbonyl carbon. That forces the weaker pi bond to break, and its electrons jump onto the oxygen, making it negative. Step 2, that newly negative oxygen immediately grabs a proton from whatever's around in the solution. That's it. Attack, then protonation. You get this, you get the whole chapter. Okay, so with that core mechanism locked in our brains, let's see how it actually works in the specific reactions that CUET examiners love to ask about. This is your go-to checklist. Think about it. Each of these is just a different actor playing the same role of the nucleophile. With HCN, the CN attacks, and you get a cyanohydrin, which is awesome for adding a carbon to a chain. With NaHSO3, you get these cool crystals, which is a neat way to purify stuff. Add an alcohol, you get an acetal, which acts like a bodyguard to protect the carbonyl group. And with ammonia derivatives, you form things like oximes, perfect for figuring out what you started with. It's all the same mechanism, just different results. Now, here's where it gets really interesting, especially for your exam. Reduction and oxidation are what really separate aldehydes from ketones. If you reduce them with something like NABH4, aldehydes will give you primary alcohols, but ketones give you secondary alcohols. But the real difference maker is oxidation. Aldehydes oxidize super easily, giving you that beautiful silver mirror with Tollens reagent or red precipitate with Fellings. And ketones? They do absolutely nothing. This is the whole basis for telling them apart. Pay attention, this is pretty much a guaranteed reasoning question. Why are aldehydes more reactive? Two simple reasons. First, the electronic reason. Ketones have two electron-donating groups that push electron density towards the carbonyl carbon, making it less positive and less attractive. Aldehydes only have one. Second, the steric reason. I mean, just look at it. Ketones are bulkier, they're more crowded. This steric hindrance makes it physically harder for the nucleophile to get in and attack. So less charge and more crowding make ketones less reactive. Simple as that. All right, theory's done. Time to switch gears. Let's arm you with the tools, tricks, and practice you need to absolutely crush these questions in the exam hall. This is where we turn that knowledge into actual marks. We all know that memory can fail under pressure, so let's use some tricks. For Tollens test, just remember, aldehydes add a silver lining. AAS. Easy. Now for the reactivity order, a super common question, just remember the word FAK. Formaldehyde is the fastest. Then, other aldehydes. And last, the slowest, are the ketones. FAK. You won't forget that one. Okay, time to put this into practice. Here's your first question. Which of these will give you a silver mirror test? Go ahead and pause right now, think about it, and then we'll check the answer. Ready? The correct answer is C, ethanol. And why? Because the silver mirror test, which is the Tollens test, is positive only for aldehydes. The other three options are all ketones. Ethanol is the only aldehyde on the list. See? It's a direct application of what we just learned. Let's level up a little bit. This one's a bit trickier. Read these two statements very carefully. Is the first one right? What about the second one? Pause again, think it through, and then press play. So, what did you get? The answer is that neither of them are correct. Statement 1 is flat out wrong. We just learned aldehydes are more reactive. And statement 2? Oh, that is a classic CUE trap. It's nucleophilic addition, not substitution. We're adding across the double bond, not replacing anything. This is why you have to read every single word in the question. Okay, I need you to listen very carefully now. These are the 5 traps that students fall into year after year. Let's make sure you're not one of them. Number 1, forgetting these tests are for telling the difference between aldehydes and ketones. 2, mixing up your products. Aldehydes reduced to primary alcohols, ketones to secondary. 3, confusing the electronic and steric reasons for reactivity. 4, forgetting that the real attacker is the ion, like Cn-, not the whole molecule. And the biggest one, number 5, calling it electrophilic addition. The nucleophile attacks, so it's nucleophilic addition. Please don't make these mistakes. We're almost there. Let's wrap this all up and consolidate everything into a super quick, rapid-fire revision. This is exactly what you should glance at 5 minutes before you walk into that exam hall. Ready? Let's go! Carbonyl carbon is electrophilic. It gets attacked by nucleophiles. Aldehydes are more reactive than ketones. Tollens test means a silver mirror, and it's for aldehydes only. Felling's test means a red precipitate, and it's for aliphatic aldehydes only. NABH4 is a reducing agent. It turns a C double bond O into a C single bond OH. And finally, the reactivity order. Formaldehyde, then other aldehydes, then ketones. Got it? And this right here, this is the main takeaway. If you forget everything else, please remember this one sentence. The carbonyl carbon is positive, and things with extra electrons attack it. This single idea is the key to this entire chapter. So, how did you do on those practice questions? Did you get both of them right? Drop your score in the comments below, whether it's 1 out of 2 or 2 out of 2, be honest. It's a great way to see where you stand. By getting through this and understanding it, you are genuinely one massive step closer to becoming a CUET topper. If this explainer helped things click for you, make sure you subscribe, because we're going to break down every single important chapter just like this. And next up on the list is carboxylic acids. I'll see you in the next one.